A couple quick announcements before we get started. Do need to turn in graded problems, so get them over to Nathan as we go here. But I'll say a few more announcements while you do that. So graded 7, of course, will be next Friday. Due next Wednesday. But there's no class on Friday because it's Veterans Day. So there's that. I also posted the project descriptions. So if you look at the top of the Gaucho Space page, I posted them last night. You'll see the full project description for each group. Okay, so if you're in the group on computational complexity, if you've looked at it, there's a bunch of questions about computational complexity. And the project is basically go through the questions, but you don't have to answer all the questions, and B, you can answer the questions that aren't on there. The goal is not to just answer them like, okay, number 1, the answer is 5, number 2, the answer is 3, or whatever. The goal is to learn something and do a write-up. So when you do your write-up, there's a project wiki that you're going to do your write-ups on. You're not just writing it, okay, the answer to A is this, and here's the work that I'm showing. No, you're writing it up with paragraphs and explaining how to do these kinds of problems. So not just answering your problems, but sort of using the problems that I gave as an avenue towards doing like a formal write-up, like writing a report. The idea is that someone else who doesn't have the list of problems can look at what you did and figure out what's going on. So it's not just the answer, you have to write the questions that you're solving and give a little bit of context as well. These projects are hard. I'm expecting that most people are going to want to come to office hours with their group at some point in the next 3 weeks and meet with me and just say, okay, we've done the first couple parts, but we got stuck on this. Want to get an idea of where to go from here. I'm expecting to get stuck at some point on most of these projects. So plan on stopping by office hours. Plan on getting some help outside of class, because I don't think maybe some of them are easier than others, I'm not sure, but I think most people will. So you can get started on that whenever you want. You also do a presentation the last day of class, and you post on the wiki. And those are the 2 components. And you get a grade, so that's always fun. What other announcements? Maybe that's it. Make sure Nathan gets your graded problems if you just walked in. But what are we doing to start with? So I've broken this up. You guys don't have group names yet, so we're going to do a lot of group work today. The first step is you need to come up with a group name. So you can discuss that, exchange contact information with each other if you haven't already. But since you have new groups, you need to do new group names. But for now, we'll just say 1, 2, 3, 4, 5, 6, and 7, the same as the project numbers. And these are part of what you're going to work on. These were some of the homework questions. So your group has a couple of homework questions that you're supposed to write up on the board in your particular place, but then also you're making a poster. Poster's on the new stuff on section 7.C, or sorry, 7.B. So let's read through this first. A volunteer with a good voice who wants to. You don't have to have a good voice. Just any voice is fine. For 7.B, just read the setup for us. How's this section going to work?
Okay.
All right, Brian, thank you.
In this section, we let transformation from R2 to R2 be a linear transformation with the following properties. A, in the direction along the line y is equal to -3x, the transformation stretches all points by a factor of 2. In the direction along the line y equals x, the transformation keeps all points fixed.
Okay, cool. So this is describing for you in words, at least, a linear transformation. Thank you, Brian. So you're supposed to, for 7.7, draw what happens to the house on the next page. So you can see on the next page is a picture of a house. Show what the linear transformation does to this house. Okay? I didn't tell you a matrix for it. I didn't tell you a whole lot of information. I just described it in terms of stretching in these directions. But show what happens to the house, and then answer 7.8, what happens to these 2 points, and then find the matrix representation. So we're going to work on this for maybe 20 to 25 minutes or so. And so, first of all, group name, that's the most important. Next most important, write down your homework problem. Just send somebody up to write up your solution to these. And on here, there's a picture. This is 7.7 and 7.8. And there's a picture you can show what happens to the house. You can also show what happens to the 2 points that I've described. and then down here, show your work for how you came up with the matrix representation. Okay? So we're going to take a lot of time on this. This is actually going to be a kind of a longer group work period than usual. So I'll set you loose on it now. I'll set my timer for 20 minutes. If we need to add some time, we will. As we go, we're going to be handing back some papers to you guys as well. Did you have any announcements, Nathan? No. Okay. All right. Great. Cool. So begin. And tell me you can write your group names up here as you go. So let's see. 20. Start. You guys all know each other? Do you know each other's names? Alright, well that's the first step. What's your for you, Ashley? Oh, you pull up here. You gotta make sure you know it.
Into what?
Intuitive. Sorry, diagonal.
You guys know each other's names?
I miss like what you do with the diagonal matrix, but they're just doing it by hand.
Yes. Right.
Yes.
That's what I meant by that.
Thank you.
Do you guys know each other's names here? Roughly? What's his name? What's his name?
Yeah, I think there is 7 points.
Okay, awesome. You guys know names? Okay. I can help you answer these. We know that. Do you guys know names? Do you have a group name yet? Do you know each other's names at least? Okay, awesome. Yeah.
If you write, this is permanent, like this count is equal it's one bit there. Yeah, here. I kind of like identity matrix. How did you prove that? What was your
Son.
Oh, those heats are ones. I got that for 7.5 E. You can set the equation for E, I got stable.
Do you want to
So we got what you got there. Yeah. I got there.
Just rearrange the seating so it's
Oh, 7.6. Sorry, so groups 7, 6, and 7. I guess I got that wrong. So sorry, you guys were 7.6.
Yeah, I think that if you use the property of the right?
Let's see,
It's multiplies the row by the amount.
yeah.
If you just maybe multiply it to
George.
Oh, you're talking about oh, B. These are already true statements, right? Yeah. Okay, so then this would just be.
Right. Let's see. Do you guys have a new name? New group name? Still working on it? You know each other's names, please?
Please no. Yeah. It's just a number.
Jason Corbin?
Those are the determinant of an elementary matrix.
So you guys have your representative up here.
I'm still very dense.
You guys have a representative up there as well.
Any elementary matrix? With elementary matrix is something that's one move away from that.
Just yes?
Like elementary matrix.
Nathan, you could put a rest over her.
It's at one of those. One or zero.
Hold on, I have it working here.
Elementary. Yeah. Because what's happening when you switch
Is this the second page of yours?
is one or less moves away, which would mean the determinant of elementary.
You guys are number 4?
I don't know, I'm asking. When you're switching the rows, you're doing C, B, minus C. Yeah, I don't know. So if the elementary is I guess it makes sense. Yeah, we're trying to figure out about the BD wouldn't be wrong.
Alright, where are we at here? Yes, number 1, okay. That's a little surprising, isn't it, huh? What were you gonna guess if you didn't actually figure it out?
Which makes sense why it's just K.
Yeah, and if you didn't think about it, you probably wouldn't guess that it would be that. And then yeah, so you applied the logic correctly for showing this. Did you come up with a group name yet? Do you know each other's names? First of all, okay, yeah, I asked that already.
Yeah.
No group name. Alright, well fine, you can think about
Yeah,
it.
so if it's only one move.
But yeah, so the main focus is on this one with the house. The main focus is on this picture with the house. What's this gonna look like? How can you figure that out?
These are all identity of one. That's what I mean by the one.
Pictures developing.
Away from that.
Wait, you had a picture, right?
That all makes sense.
Starting to. I know, wait, who was it? Oh, you had something too.
So I think we'll just say 7.5 is just K.
Yeah, well, we can assume D.
Okay, so you figured out the matrix. You did this part first. Okay, alright, well, you're cheating.
This one's probably KD because it's still safe.
Does it make sense, the picture that you came up with, in terms, like, based on the description? Or is it unexpected?
I think it probably is.
Does it look like it's being stretched in the way described, what she has drawn here?
I think that's No, I think it is. Yeah. So we got 7.5. So I think you're right.
What did you guys do? 7.5
Yeah.
Yeah, this is a different way. I haven't described it.
7.5C is
More like stretching.
H, D. Yeah.
You guys have anybody trying to draw a picture yet? This is gonna look like what the house is gonna look like. That's the first step on this one, is trying to draw a picture. So you can, you have the house there, right? What does the house look like? I see you've sort of drawn those two directions. factor of 2 in one way and stake fixed in the other way. It doesn't have to be a good picture. I mean, the first one is supposed to be like just use your intuition. You can calculate it also, but it's supposed to just be like what does it look like? In part, in 7.9, figure out like at least get like a kind of intuitive picture for what I mean by this. It's kind of stretched in one direction and fixed in another.
I just use probably
Which one are you guys working on now? Yeah. Okay.
yeah.
So you're starting to draw a picture.
Just map it.
Yeah. Okay. So you're cheating. You're going straight to 7.9.
Supposed to just add.
Well, let's see. I wanted to look at what Shane is drawing here. Because I like the way you're thinking about this. So you drew the two directions.
This matrix will be
So tell me what's going on with this line segment.
Yeah,
You're kind of getting at the heart of
So
that.
if you be determined.
Can you explain what your thinking was, why you drew this way?
One row to another row. Yeah. Yeah, this matrix 1, 1, 1.
Oh my god. Oh yeah.
Yeah, it's just that I have to pay out of the first row.
Can you do other parts of the picture, like kind of similar logic? You gotta, I mean, that's a great sign. That's an awesome observation to think like, okay, well, this part gets noticed on that one. Yeah, because that's not the Okay. Oh, wait, hold on. Okay. Yeah, I see. I think I probably meant to do 7.6, but that's okay. You're answering the question. What was it?
We're doing. I'm doing G right now.
Oh, okay. Okay, cool. Yeah, no, that's great.
No, wait.
I have another group.
So minus 3.
Yeah, how are you guys starting to draw this picture?
Yes, and then you stretch it along.
Okay.
What was the word for? Yeah, and also so long. Yeah. Just like give an example.
So let's see, so you guys might get something where did you come up with this? So do you guys draw the line what it says? Or are you worried about it?
But does the point on that line, does it not come up with X?
Yes. So this is do what it said, stretch it by a factor of 2 in that one direction and fixes the other direction.
So what does that mean? It stretches
basically, if it stretches
So you don't need to get it exactly right, especially because it's you draw this
along this line, should go out to one side, right? Stretch it like so then you can do it as like this, say that
it's gonna be like a work.
it's like that's the transformation.
Okay, so it'll be like.
Yeah, so can you explain?
So maybe you could like rotate.
Yeah,
Like this point will be here, and then you can do that for this point will be here. Maybe make a well,
like the original line would be here, so everything is like tilted this way.
So if you just like a couple distances, like
Peak kind of wide, maybe around there all along the line. Like instead of being oriented on this line, how it tilts. And then we'll stretch it after that. Because if it was stretched by a factor of 1 in that direction, it would just be tilted. So we could stretch it for a second.
I'm sure that's
So our two vectors are.
So how do you stretch in a direction?
okay, so you're doing like you're doubling that distance.
But if you stretch this peak in this direction, it would be
And what about this one? That's
yeah. But so you would just pull this point up here. Yeah, that's what I'm saying. So like, how do you?
Well, we can use.
No, we have like you can use test points to see where.
Well, we can use. So you could say it's like this is in your combination of something anything times something. And if we change that.
Like when you stretch on X direction.
Yeah, we have to like.
So it's not gonna stretch in this direction, but like it'll stretch like horizontally this way.
But then it's on this line. So we can represent that as a vector.
Does that make sense?
You want to try to do 7.3 first to find out the we can figure out what it looks like.
Well, okay, so we have one vector, one negative, one
Yeah, I was commenting. Cool. Can you explain your picture here?
It says a long life of X all comes with X too, so I don't know how you keep putting those.
Yeah, I mean that's what I'm describing, right?
So we use linear combination of these.
So let's try and go like there's certain points that I see that Eigenvalue you're kind of drawing this also like kind of maybe it looks like it's going to come out in a kind of similar way, and I just sort of wanted to like think about it. Yeah. So I noticed that you made sure this point kind of stays the same. Yeah, because it's on that line. It looks like you sort of see what's double. Maybe this line got extended for like a sensor with that. But it seems like that kind of logic is making sense, and you're sort of starting to end up with like a similar picture. So for 7.7, you know, I just wanted a picture. It doesn't have to be like precise enough to figure out the matrix or anything. But then in 7.9 is where you so whatever logic you use, just like thinking of it as stretching, or like that's logic. It's probably kind of too hard to like draw it exactly and precisely right anyway. So yeah, I sort of want to see that information. That's what I'm really going for on this first one.
And if you're saying like for any value y is equal to up the number, you can say like all the after we get to power u,
Trying to find this point and the linear combination should be possible.
So you're trying to see where that point goes when you just highlight it?
Well,
hoping to write this point as a linear
It's not just on that line though. It's like
vectors, and then with that,
so like if you erase these coordinate axes and then you just have these coordinate axes, it would be like stretching it.
Okay, yeah, that makes sense. That's kind of similar to some of the problems they're doing like last week. Okay. Are there a few points that you can kind of say exactly where they go right away? I noticed Joseph had drawn the two directions here, and Ryan also. One day gets fixed and one day gets double.
So then,
Are there some points that you can say right away where they go?
Well, I can take it back.
like this point right here corresponds to some corresponds to some like y equals x, right? So then this will remain the same in relation to y is equal to x, but along here it will stretch twice. I don't know how that'll end up.
Okay, so I'm not going to stop us completely here, but I think that's maybe a signal that now it's time to start writing up your results on the graph paper. So like I've been telling some groups this, for the picture in 7.7, it doesn't need to be very precise. I mean, if the way that you figured it out was by using matrices or doing algebra, that's great. Like I said, it should be a combination. You use a combination of your intuition. And I saw a lot of people just sort of like said, well, it stretches in this way, so it should look like this. That's great. That's the kind of thing that I'm looking for in the picture. Or if you do calculations, show us how you use the calculations. But I just want the picture on the top half. And then as you figure out what the matrix is, you can write down the bottom half. So let's take maybe another 5 or so minutes to start getting those posters ready. Okay, 5 or 10 minutes to get those posters ready. Alright, so it's time to clear it off, get the poster going. So you guys work on that.
Theoretically, like number 1.
Yeah, equals 0
Well, yeah.
So you have to make
There's why we're in here. We're all good on names? Yeah. What's his name?
in this case, I'm making it.
What's her name? Well, I know you know her. So make sure you know just
Find A and B.
You're going to be working with this one the rest of the course. Open up the lines. You're going to be doing projects.
It'll be the same A and B, but
different transformation.
yeah, okay, I get what you're trying to do.
Like that one.
Yeah. That makes sense. So we'll have a different set of A and B for that.
Where's the rest of your group? Who's in it?
Yeah, no, it makes sense. They'll do the transformation. Because if you write it up as a transformation, that comes out as a straight transformation. Well, just to shoot it.
Yeah, that's what we're doing.
Alright, let's see. Who's got the picture? Who's gonna do some magic hands that can draw this picture?
Basically, we're finding this point as a combination.
So why did we ever need to do this? Yeah. Why do we even need to do that?
Should I be the one to try? I feel like I like feeling reluctant to draw it.
Right, which means
Alright, and you're the one who-
that we know what to multiply the data.
So you're gonna do A0, B, and C. So then why did we need to do that?
Yeah, so that should be right.
Yeah, okay, so if this wasn't a 0, then maybe it would be. So if we're doing it for this one, then what is this? Okay, it just happens to work out.
Well, so you use
It's like, think about it, think about it as coordinate axes, then like, this point should extend out parallel to this, here. Yeah.
Okay, so that one is why he was saying the one that you don't even need to look at, you're already on that. Two separate things.
Okay.
Which is why this one's
Okay,
part.
so we're doing 7.7 first.
Yeah. I want to each do like a
I'll do 1, 0.
So we want to do 0 and 1. You want to do this one right here, 0 and 1. I'll do 1 again.
Should I should follow these lines.
So we just set up as a
-1.
Alright, let's move it back.
sorry.
Draw the original house.
I keep getting you confused.
Yeah, draw it in different colors.
What's your, is this your actual name? Okay.
We're finding like the
Who
translation.
is Lee? Here?
That's fine. Well, that's using the
Okay, you basically.
yeah.
I like the one we already solved.
Is Lee here?
This is like this point.
Oh, there you are. Okay, sorry.
Yeah, like you know what that's like representing, no?
Well,
Well, this is representing like this statement is representing like this one right here, and like how you would get to it using your combination of these two.
sorry, were you in this group or were you in
The vectors, so like one, this is like their line. So this is just saying like, yeah, what's the thing? So we know that, so we can set it up in the new one where you ask me
Sorry about that.
that one. And since it works out, we're
Okay, so that means
in this case, we have to
decided to finish up.
put in a more complicated one where they it'll be more.
Okay, I can see people are still drawing their pictures and writing down their matrices, so give us a couple more minutes, but that means wrap it up now. Wrap it up as quickly as you can now. And we'll start doing presentations in a second. I'll give us maybe 1 or 2 more minutes. If your picture isn't great, that's fine. You guys need to start drawing. I can see you're all working individually, but we're in a group for a reason.
Okay, I got one half. Okay, I got.
Yeah, not too free, not too.
Doesn't have to be perfect. See you and picture in the next 60 seconds. General idea. Either way.
Oh, yeah.
You can just explain it. You could say just do all this. Okay, so make sure when you get to this point, you write it down. Yeah, you just plug in A, B, and then you can
So for half points in general, there were very little. Okay, so while people finish their drawings, I'll just ask that they quiet down while people are finishing their drawings here, because I wanted to talk through a few of these problems that you had for homework last night. So there's a few that in particular that I think are pretty important, and the ones that group number 1 did. Do you guys have a group name yet? Group number 1?
Number 1 group.
The 1 group?
Number 1.
Number 1 group. Okay, so group number the one number group. Group number 1 is the number 1 group. The number 1 group. So okay, so let's see. Everybody quiet down so they can talk about their results. So this is so shh, don't make me shush you. So can you explain what happened here at 7.4c? So this is elementary matrix which adds k times one row to another row. What is the determinant of that matrix? And then 7.5c. Why don't you explain that? So how about Jasheen? Can you tell us what's going on here on at least 7.4c?
Do they go to the board? Huh?
7.4c, it's just like I just find some examples to find out what the determinant of the elementary matrix, which can add k times one row to another row to figure out what's it. So I just like find some examples to find out it.
Okay. There's some examples, and you found, looks like you're saying determinant is 1. Is it always 1, or is that just because of this particular case?
And it's always 1.
Is this what other people had concluded? For 7.4c, the determinant of a matrix which adds k times one row to another row. It's a little bit unexpected, right? Maybe a little bit unexpected. You'd think that this would have a determinant that's not just 1, but it turns out if you try a few examples, you can convince yourself that it's going to work out like this. And so let's see, on 7.5c, so Tinyao, what does that mean if you actually do this operation? How does it change the determinant?
I mean, the determinant of the matrix, it gets from the elementary matrix. So it's just if you do the elementary matrix x k times one row to another row, it doesn't change the determinant of the original matrix M. So it's just the D.
Okay, that didn't change it. So again, you're using this property when I said it's one of the most important properties of the determinant, right? That determinant of, okay, this is the elementary matrix which does something to M. Then the determinant of E times M, so this is after the operation has been done. That should be determinant of E, which you said was 1 times determinant of M, so it didn't change the determinant. Okay, awesome. Let's see, number 2, I think part E was a little bit, 7.5e is a little bit unexpected. So let's see. Evelyn, I saw you wrote this up. Can you tell us what happened in 7.5e?
So basically we had to find the determinant of like k times a matrix, and we found that it would be for n columns, it would be k to the n times the determinant of the original matrix, and we just did some work to find that.
Okay. This also seems a little bit unexpected, right? Do you agree? Maybe you just thought, oh, it would just be k times the determinant, but yeah, why is it? Why did that happen? Steven, you're eager.
Yeah. Well, I think we showed before that if you just multiply a single row by k, then the determinant is multiplied by k. So like multiplying every single row in the matrix is like doing multiplying it by kind of an elementary matrix for every single row. So it makes sense that it's scaled by k with the number of rows.
Okay. So yeah, so you're multiplying by k for each row, since you're doing that like that kind of operation n times for this n rows. Yeah, Jerry. Yep.
Also, like if you think about like geometric meaning of definition, like if you initially scalar something by a, but now you scalar something in both direction by k times a, in terms of area, it's going to be k squared because you are doing scalar twice. And if it's in 3-dimensional, you get cubic because you're doing it to volume. So that kind of makes sense there as well.
This is interesting. So he's saying, look, if you stretch it in one direction by a factor of k, fine, you're multiplying the area or the volume, or in higher dimensions, whatever volume's equivalent is, hypervolume, multiplying it by k. But then you do that in each direction, well, you've done it in n directions, so it's changed the volume by k to the n if you've done it in n directions. It's actually maybe a good segue into right? Yeah. So that's maybe a good segue into the problem that you guys are working on, this 7.7, 7.8, 7.9. I didn't ask this question, but what do you think the determinant of the matrix you found in 7.9 is? Don't calculate it. Don't calculate it. Before you calculate it, can you say what the determinant is going to be? Is it obvious how the area changes? Maybe I'll leave that as a question to think about for a second, but as we go through some of the rest of these. But is it obvious how the area changes and what the area distortion factor, the determinant, is going to be for this? And we'll think about that. Let's keep that in the back of our minds. So I see also group 2 showed us how to find the determinant of the diagonal matrix, and it looks like it's very easy. Just multiply those entries. Great. Let's see. I just want to go through maybe some of the most surprising or interesting ones here. How about for letter number 6, group 6. So let's see. Siki, could you tell us what happened in letter 6? How did you figure this out on 7.6? Wait, hold on. Which one were you guys? 7.6 E and F.
I subtracted the first row from the second row, and I got a row of 0, and obviously the determinant of the matrix is 0. And the second matrix, I find the transpose of the matrix, and I got the 2 rows that are the same at the end, and so I can get a row of 0 at the end.
So let's see. I want to see if there's questions on this. How he did this. Why he got what he got.
I use the property in
Oh, remember what property B was? Property B was that the determinant of a matrix is 0 if and only if, well, all this other stuff in the invertible matrix theorem, in particular that M has, determinant 0 if and only if M has, or you even wrote that, if and only if M has no inverse. So, can somebody explain how it's obvious in that first example where the 2 rows are the same that there's no inverse? Why is it obvious right away that there's no inverse to that matrix? The 2 rows are the same. Yeah, Peter. Say it again?
Linearly dependent, so there will not be inverse, and then the determinant will be 0.
So what's linearly dependent in that case?
It's like the 2 F of the 2 columns are the same, so it's linearly dependent.
Well, so you're saying it, and I'm being very precise about the language here, and I know exactly what you mean, but I want to make you say it. So when we say something is linearly independent or dependent, we're talking about a set of vectors. So what set of vectors are you talking about here?
It's like first and the set of like first column and second column are linearly dependent. So determinant is 0.
Okay, great. So I hear a lot of people often saying, oh, the matrix is linearly independent or the matrix is linearly dependent, but it's not a matrix that we're talking about. I just wanted to make you force you to say it that way. The columns of this matrix are what are linearly dependent. And you said, look, even just the first two, it's obvious because they're the same, right? One is a scalar multiple of the other. In fact, it's one times the other. So great. These are the columns are linearly dependent, and so that means that's part of the invertible matrix theorem. So that means that that certainly the determinant has to be 0. So that was what you did. You could have even just skipped from here to here. Yeah.
And then for the first one, can we say that the transpose of a matrix has the same determinant as the regular matrix? So if we took the transpose of that matrix, then we would get a column of zeros, which means that the columns would be linearly dependent, therefore the determinant is 0.
Yeah, that kind of works for either one of these, right? Because if you take the transpose of this, you'll have two columns that are the same. Do the transpose of this, you have one column of zeros. Either way, the columns are going to be linearly dependent. So yeah, same exact logic is going to work here. Cool. Yeah, I like that. There's different ways you can approach this, but you're using the properties. That's what's important. How did you know that the, so Siki said this, he said, okay, well, I take a little bit of issue with the way you've written this here because these matrices aren't equal, but the determinants are. I think that's what you meant probably, right? So let's just write that in. Determinant, or actually another way that people sometimes do this is if you're taking the determinant, they won't use brackets, they'll just use vertical lines. So that just means if you write the matrix instead of brackets, you just write your vertical lines, it's implied that you mean the determinant of the matrix rather than the matrix itself. So whatever, that's another notation. So fine, you meant these determinants are equal. Now you said you did a row operation here. And how did you know that after this row operation you were going to get the same determinant after this row operation? Now we saw that some row operations change the determinant. Row operation doesn't always give you the same determinant. Okay, well which one was it? Which row operation did you do here?
I said rho 2 minus rho 1.
Okay, so this falls under your category, right? Where you add a scalar multiple of one row to a different row. And so that's one that does have determinant 1, so these would have for sure the same determinant. So I just wanted to point that out. Some row operations do change the determinant, so you can't always just say, oh yeah, they're definitely equal, but then again, it shouldn't change whether it's 0 or not. Right? Wouldn't change, you're either multiplying by a non-zero scalar k, you're multiplying row by k, or you're multiplying by -1 if you swap 2 rows. So cool, this ended up being a good one to talk through. Oh geez, okay, we're almost out of time. So maybe I'm going to save these posters for next time. I think it's probably a reasonable way to go here. But let me have group number 7. Do you guys have a group name yet?
Yes.
What's your group name?
Swiftly improvised xylophone.
Wait, say it again?
Swiftly improvised xylophone.
Xylophone.
Yes.
Swiftly improvised
xylophone.
Wouldn't that be their name?
Yeah. Well, I mean, we're 6 people.
Oh, okay. S-I-X. Okay, well, so 6 people. All right, fine. That's going to be confusing. So group 7, that's actually group 6. How did you do this? I like the way you've written it actually a lot here. So Carrie, can you tell us what you did?
We know that from 7.4a, we know that the determinant of an elementary matrix which swaps 2 rows is -1. And from this matrix, we use 3 swaps, like odd numbers of swaps to get to the identity matrix. So that is the determinant of this.
Okay. Yeah, I really like the way you wrote this. The determinant of this is the negative determinant after 1 swap, which again gets multiplied by -1, again gets multiplied by -1. We sort of thought about this at the end of last class. Is there maybe a way to go from this matrix to this matrix with, let's say, instead of the 3 swaps that you did, maybe 4 swaps in a different order, different ways of swapping that? Are you sure?
Yeah.
Why are you sure? You sounded very confident. Why did you say it's not going to be possible?
Oh, no.
You spoke up. The confidence came from behind. You said it, but the confidence came from somewhere else. swap a row with itself, is that going to change the sign of the determinant? Alright, so maybe we shouldn't allow that. I won't count that as a swap. Yeah, could you, so I mean, it's sort of like you're reordering the rows, right? In a way, you're reordering these rows in a certain way. We took the third one and put it first. This first one goes second. The second one goes fourth. You're reordering these rows. And you did it in a certain order. But you could imagine maybe taking different steps. Like the first step you did was to, was what? You switched rows 2 and 4. But maybe someone else would look at it and say, oh, I'm going to switch rows 1 and 3 first. Or whatever. There's different ways you could think, different orders in which you could think to swap the rows. Is there an ordering in which you could swap the rows that would give you, instead of 1, 2, 3 steps, 1, 2, 3, 4 steps in some other path?
No, but you can get 5.
People are shaking their heads. Well, let's see, somebody else who felt confident. Was the confidence coming from David? Why do you say that? Why are you skeptical?
I think another kind of reason you can come with it is if there's some even way to swap it, so you can say that the determinant would be equal to 1. But if the determinant's equal to 1, the determinant's equal to -1, because we've shown there's an odd number of ways, then clearly there's a problem there.
So if there were an even number, you're saying that we would have gone through an even number of multiplying by -1, and we would have
And the
gotten
problem
to
here is we don't know if it's
negative
negative 1 or not. We couldn't just like.
But if we show that there's a way to do it on the
Yeah, you can calculate it from the first and say it's possible, but here we're using that conjecture.
I'm saying I think it works.
So okay, so let me sort of maybe take this into put this in perspective, because you're using the logic that says, okay, well fine, if you did swap 4 times, then the determinant of the original matrix would have been 1, and we just showed it's -1. And so you're using a property that I told you, right? That anytime you swap 2 rows, you multiply the determinant by -1. So we're being a little bit circular because you're using this thing that I haven't really told you why it works exactly, right? But this is maybe a way of sort of seeing that, yeah, it's not possible to swap the order using 4 swaps, because you would get a different determinant. And presumably, I haven't lied to you. The determinant is a real thing, that you figure it out the way I said, the properties I've told you aren't lies. So in that sense, yeah, kind of shows that this has to work out to an odd number of swaps. You couldn't do swaps. Okay, so I'm going to save your posters. We'll do these on Monday. Have a good long weekend. I'll see you guys then. Awesome.